Hi there, everybody. There's some math I want to talk about today, and I was all sort of gung-ho or whatever, and but I got delayed by about an hour, so I kind of lost my mojo, so it's gonna kind of maybe suck today. I don't know. Sorry about that, but I want to try to put out some of the stuff I was thinking about. One, because it might interest anybody else. Two, maybe, I mean, probably people have already thought about all the stuff I'm thinking about here. And so possibly, you know, somebody who knows more about it than me can leave a comment. Yeah, those are the main reasons, I guess. And this was pretty interesting, this they say hyperboloidal gears. I don't know why they don't call it, why it's not called hyperbolic. But I was doing some of that stuff, and it relates to the stuff I want to talk about today. But, so I want to talk about knot theory. I want to talk about what apparently, I guess, Einstein was working on towards the end of his life. I don't know. But anyway, so 1935, Einstein and Rosen put out this paper, the paper that introduced wormholes. And I talked about this stuff a bit in a recent video, but apparently, according to, well, I guess that the motivation for the idea was about viewing the elementary particles as wormholes. Or singularities, wormholes, whatever. I mean, if you have a high energy photon, a gamma ray, it can break into an anti-electron pair, and well, I don't want to go too much into all of that. It's all just speculation anyway. But yeah, this idea that elementary particles could be singularities is something that's interesting to me. Now, knot theory, I believe it was 1988 when Witten published a paper showing a correspondence between knot theory and quantum field theory. So yeah, physicists have been interested in sort of digging deeper there and trying to figure out more, if they can, about why knot theory is related to that. Now, I wasn't there at the time. John Baez has this blog that, if you go to some of the early entries of the blog, it's supposed to be one of the, or if not the earliest blog that ever existed. I believe it's called N Category Cafe, but I'm not sure if it was named that back in the day, or if it's always had that name or what. But there it is. In Category Cafe. And there's, I mean, John Baez is kind of the keeper of the flame, if you will, but there's lots of other guest posts and stuff. Anyway, so if you go back to the very beginning, he talks about knot theory and a bit. But anyway, so my idea is, well, essentially maybe the elementary particles are sort of knots in space-time. You could imagine, like, so if the fundamental unit of energy is a wave in space-time, so actually like a gravitational wave. If you had a little volume of space and you decided to put a bunch of energy into that space, so lots of gravitational waves, I guess, but space-time waves, you can imagine like this complicated mess happens, but certain spots, certain little pockets might be sort of swing very much in the time direction. What I mean by that is that if you and I were separate observers, but we're at rest with respect to each other, then we agree on this inertial reference frame, right? And anything, if we observe anything that, from our point of view, has velocity, is moving around, we would look at it and say, well, their clock is running slower. So we would never look at anything and say, oh, their clock is running faster than ours. That's not going to happen. But we might look at something and say, if it's moving from our point of view, we would say that their clock runs slower than ours. Now, if that sounds alien to you, look up. This is just special relativity stuff, right? So, anyway, so so certain pockets of this. So I'm imagining it's kind of like you might imagine a particle accelerator, or just blasting like high energy photons in each other's direction and seeing what happens. Except we're just doing this with space-time waves, gravitational waves, whatever. And so if you have waves, well, you have certain areas. And so I'm kind of, let's be fair, I'm kind of starting to talk out of my butt here, but you might have sort of pockets where the clock is running slow. Regions of space where, the clock appears to run slow. So curvature, space-time curvature. Okay. At an extreme, if we saw a black hole, or we're observing a black hole, say you and I are stationary with respect to each other, so we are we agree on our clocks, and we agree on our rulers, so the distances and everything, but we are orbiting a black hole, and so at the event horizon, from our point of view, time goes to a stop. So that would be the extreme. And the mathematics here is hyperbolic geometry. You can sort of understand, let's say, talking about velocity and inertial reference frames and special relativity, you can understand it as sort of moving on the surface of a hyperbola. And so a hyperbola, now I'm going to try drawing here, and this is kind of new to me. Let's see what we can do here. So let's get rid of this one as well. This is actually a hyperboloid shape here. I'll just show you how this is made roughly, although, let's see, I was following along this tutorial, but if we go back, I started as a cylinder, and then I rotate the circles, if you will, and it forms this nice. This is a hyperbola right here. Okay, viewed from the side. Interestingly, if you take a cube, okay. I'll just try to say this really briefly, so it might sound complicated. But if you took a cube and, say, you put it on a desk and with a vertex pointing down, and so the opposite vertex pointed straight up, and then you gave it a spin like a top, in the middle, somewhere in there, this rotation, it forms a the shape of a hyperboloid. So weird and interesting that you can get it from a cube as well, but that's sort of for another day. I feel like there's some kind of deep, it's telling us something deep about mathematics, the fact that the cube can do that, but I don't know what it's telling us. I think about it sometimes. It's an interesting thing to think about. Okay, anyway, so this is just the cylinder is basically just twisted, and it forms this hyperboloid. And yeah, whatever, let's get rid of it. And so we were talking about a hyperbola. So let's see if I can do this. I think we need to add a grease pencil and go into this draw mode thing. Yeah, okay, so the hyperbola, you can imagine a hyperbola. This is an asymptote. If you don't know what a hyperbola is, I'm sorry, you're gonna have to look it up. And so here's like the what do you call it? It's got a name. The 0.10 anyway. And so it follows these asymptotes. And so so we're stationary, we're here, this is our inertial reference frame, and then somebody else, they say, I'm going to go at the speed of light, sayonara, or I'm going to go as fast as I possibly can. And so they go what to them is half the speed of light, but then they decide, wait a second, I can still refer to myself as being stationary. And then they can do whatever force they put on themselves to go that fast. They can do it again and again and again forever. And what happens is they just keep moving along this hyperbola, going further and further that way, but they never cross over. So you can imagine crossing over as going faster than the speed of light. So you're never able to go faster than the speed of light, but you can always increase your velocity more and more and more, and get infinitely close to the speed of light. That's sort of the like super spark notes here about special relativity. Anyway, I don't remember why I was going to talk about that. Oh, but I was talking about, so energy, you sort of like toss a bunch of energy in a box, and certain pockets, the clock goes slow. At an extreme, it completely stops. And so maybe these are like elementary particles, because say like well, a proton, for example, I mean, it has three quarks in it, but eventually it's said that it should decay at some point. See, I don't have the energy for this talk. It sucks. I was so gung-ho for this. Anyway, so I'm going to skip over that because I can't explain it. But the thought experiment here is you throw a bunch of energy in a box, and these little space-time knots appear. And the thing is that for some of them, the clock has gone very close to being stopped. And so locally, if the clock is very close to being stopped, then it's like a black hole. I mean, black holes eventually dissipate as well. And yeah, I'm sorry, I can't explain better than that. But anyway, so elementary particles as knots in space-time. That's the thing I'm interested in. So how do we go about tackling that? Well, first, think about bending space. Forget about space-time for a bit. And so the simplest knot that you can have is this trefoil knot. And let's see, trefoil knot, please. Yeah, it looks like that. I mean, this is cool that it's animated, but it's also a little complicated to think about. And so you'll notice if we follow along, it goes over, under, over, under, over, under, and then where we started. So that was alternating, over, under, and it did it. I said something 6 times. Over, under, over, under, over, under. There's a chirality to this, okay? You look it up if you want to think more about that. Actually, these are 2 different chiral trefoil knots. So yeah, this is the simplest knot, other than, I mean, technically there's the unknot, which is just a circle. I'm not going to explain the basics of knot theory. You'll notice that the knot is connected to itself, okay? So these are embeddings of the circle in 3-dimensional space, essentially. And if you start listening to these talks from knot theorists, actually, I'll just mention Veritasium has a video on knot theory, and it's kind of disappointing to me because the title is like refers to knot theory as like the most useless math or something. I find that weird. Just because, yeah. Anyway. I mean, yeah, if it's connected with quantum field theory, then why would you think it's useless? Anyway, I don't think he talks about that in the video. So, yeah, but if you listen to knot theorists, they'll tell you it's not just the knot that we're thinking about, it's the complement of the knot, so all of the space outside the knot. And so can you imagine... So I'm going to get a little hand-wavy because I'm not I'm not a trained mathematician here, so a disclaimer. But I would like to imagine the complement of the knot, so all the space outside of the knot, as getting sort of twisted up. So I'd like to imagine the knot as sort of representing a twisting of space. I think that's fair, but then you have this question, because the knot itself is just this little string. It's a circle that's been twisted up. So how would you go about explaining, how could it twist, sort of represent twisting all of space? And so I'm trying to decompose the trefoil knot. And by the way, I'd like to eventually, look at more knots, but I should really start with the simplest non-trivial example. So the question is, can I come up with some equation where that somehow corresponds to a trefoil knot in some way that represents a twisting of space, three-dimensional space? And it could just be an equation that describes a vector field. Okay. And but the actual surface of the knot, it's a one-dimensional surface of the knot, could be a singularity. So I can kind of imagine two different ways. I can imagine, let's see, I can't very quickly draw the thing. Suppose this is the knot, which it's drawn incorrectly. But as you get close, so I could imagine that the vector, so there's sort of geodesics, meaning if we put a test particle somewhere in the space, then it follows vector fields and it just sort of drifts along, right? Like a test particle in a magnetic field, for example. And so I could imagine that if it's close to the string, the surface of the knot, that it follows along the surface of the knot. But I could also imagine where, oh, that's interesting, okay, where it's sort of the opposite, and these are kind of singularities, and things sort of like swing around, like almost like an orbit. I don't know if that makes sense. So imagine like coming out from infinity, we come in and we have a path. This is a geodesic, and we get really close to the surface of the knot, and we just swing around like this. Okay? We went through that loop. So maybe those are sort of complementary or dual ideas, because one of them, or maybe they both are fine. They both exist. Like you have a geodesic going along here, and you have a geodesic here. It's like a saddle point. Now, I suspect that these ideas exist out there, that's already been done and all that stuff. So if anybody knows, I'd love to hear about it. I'm also interested in kind of diving in, and this is a way to learn math, is try to figure out these things on your own as well. By the way, the trefoil knot fits nicely on the surface of a torus, so it's what's called a toroidal knot. Torus, we all know what a torus looks like, but just in case we don't, we have it right here. This is a torus. So you could draw the knot on the surface here. Very nice and uniformly. And just food for thought or whatever. It's an interesting idea. What if you scale this up? It's not going to do the scaling that I want. I want like a projective scaling where like the inside of the ring stays put and the outside scales outwards forever. As if there's a point at infinity. So another thing that comes up in my thinking, and I hear knot theorists talk about it, is sort of projective geometry, the point at infinity. They think of the knots on a three-sphere, I think. So the idea, I'm going to gloss over that. Some people will know what I'm talking about. If you don't know about it, look up about the Riemann sphere. Mobius transformations, that is kind of a fun way to learn about that stuff. So yeah, you can have a point at infinity, you can have sort of geometry at infinity. And I'm getting a little in the weeds here, but I think that's okay. Anyway, let's so let me bring in this other thing that's gonna look weird at first. I'm trying to sort of decompose the trefoil knot into smaller parts, and I think this path that's highlighted here, let me get rid of this one. This path here, I think, is a trefoil knot. I'll feel silly if I'm mistaken. But, and by the way, I mean, yeah, we can pull the knot apart and do certain things, and it's still the same knot, right? So how did I create this, and what's the idea here? Let me just create it from scratch and then explain as I go. So we'll have a new path, I believe, curve, path. Okay, I'm gonna rotate that this way. So the first thing, so I'm trying to decompose the trefoil knot into smaller parts that I can sort of take one part at a time. Trying to think of space being transformed. Anyway, so we're breaking it down, decomposing it into separate parts. So one of the parts, the first part, is basically a loop-de-loop. Yeah, so a loop-de-loop. If English is not your first language, maybe you don't know what the heck I'm talking about. But on a roller coaster, sometimes you have these sort of loops. Let me just try to make this the way I want it. Actually, that was fine, whatever. Yeah, it's kind of hard to get things exactly the way you want them here. But imagine this is a roller coaster. We go along and we do a loop-de-loop, right? A loop. Okay, cool. Let me just adjust some things. Make it a little cleaner, I guess. All right. So there's a loop, and then now I'm going to feel stupid if this whole thing I'm making actually is not a trefoil knot. I checked once. I thought, yeah, I think it's a trefoil knot. So hopefully it is a trefoil knot, or else this whole thing is stupid. But anyway, so now you can see, like, we came over here on the left, and then it went up, and then we're down here on the right in the roller coaster. And so we want to continue not over here on the right. We want to cross over to the left, and on the opposite side we're going to cross over back this way. Is that right? Yes. And so we can just go off to infinity or however far we want on both of these. So all we've done is loop-de-loop and bending over, turning on both sides, right? That's all we've done. And then we'll just bring these over and bring this over a bit. And then my claim is that now if I connect these two ends here through the loop, that's a trefoil knot. Hope that's right. I'm not going to think about it again in real time because I would probably need like 5 minutes to check. But anyway, so yeah, we just go through the loop-de-loop. Now, we could have gone off to the point at infinity and then come back, I guess. But we'll try to sort of connect these dots, I guess, just for demonstration or something. I don't know. Okay, so they're basically, more or less, they're connected here. And I think that's a trefoil knot. So this is how I think of checking that. I try to find an angle where you can count the crossovers. It is kind of hard. Also, this one doesn't need to be like that. So remember, it should go up, under, or sorry, over, under, over, under, like that. So make this a little more connected there. So admittedly, this is hard to see, but let's come in here. So it's over. Uh-oh, it's over. Oh, okay. I think I can make it so that I think this is I think this first over is unnecessary. There's like there are these Rademeister moves that you can do. I don't have time to explain it, but anyway. Let's count it as going over the loop and then under the loop. Over, is that over? Yeah, over. Under, over, under. And then I think this one maybe doesn't count. So I don't know, I think it's a truffle knot. So we can decompose this. There's a loop, there's the bending, the turning, and then there's this connecting in the center of the loop from the points at infinity. Or, I mean, there's more elegant ways of talking about the trefoil, again, like just on the surface of the torus. But the point here the reason I did this is just that, yeah, I want to decompose it. So actually what I started with before this was a bit simpler, but it didn't fully work. But I'll show kind of what I was thinking. Can we just make this bigger? And then, all right, so let's bend this a bit. And then we're going to have another path. Another path. Let's see, rotate along the Y, 90. I think I deselected it. Okay, so the idea here, it's sort of, you can think of these as two hyperbolas, even though they're not drawn very well. And they're sort of interlocked a bit. And so I was thinking, well, if these endpoints go off to infinity and then connect in some way, can I make this into a trefoil knot? Maybe I just did it wrong. Because this little pattern, this little hook, basically exists here. Like, the way I did this is I came in straight, but I don't have to. I could have come from... Let me do it on this one, actually. Yeah, it's there. How do I focus on an object? Okay. So the loop-de-loop part, imagine that as one of the hyperbolas, and then this other thing coming in as the hook. You see they're sort of linked like that? This coming up and down is one of the hyperbolas, one of the hooks, and this part of the loop-de-loop is another hook. Like here. So this sort of basic thing. So I was thinking, well, this sort of basic thing, which is like, it's kind of like two hyperbolas that are, let me fix the camera a bit here. Okay. They're kind of like two hyperbolas that are interlocked. And so can I create a vector field potentially that really just kind of represents bending of space? Or can I transform space in a way that creates vector fields that sort of correspond to these two curves? They don't have to be hyperbolas, it could be whatever. And then you can imagine sort of geodesics. So you can imagine all kinds of geodesics. Grease pencil, empty, we'll go to draw mode. I guess they revamped the draw mode here with Blender 4.3. And it takes a second to load in when you first do it, I think. Or it'll crash, who knows. But Yeah, is that gonna work? There it goes. So, I don't know, you can imagine geodesics is coming in. Flying in, and I don't know, would it twist? I think they would, sometimes they would twist, go flying through. Who knows? So, I'm gonna maybe delete all these weird paths and drawings and everything. It's not gonna get back to the cylinder, is it? Okay. Alright, 1 second, let me load in. Let me just reload this. No? Okay, we're good. There are hyperbolic surfaces here, so it reminds me of the hook thing that I just showed you. Now this is at a different angle, so it's at a 75-degree angle. So I knew about these hyperboloidal gears for some time. There's this interesting number file one here. 3 gears are possible. And yeah, it's kind of a difficult mission, basically, to get equations, and I don't want to have an equation that is like a page long. I want something that is sort of canonical, where somehow the torus, or sorry, the trefoil knot is representative of a transformation of space, bending of space, twisting of space. So not just the knot itself, but so that basically every point in space, except maybe the actual knot itself, so the complement of the knot, all of the points that are not the knot, all the points that are the complement of the knot, can be defined as a family of geodesics. So the geodesics are just, again, if you put a test particle there in a magnetic field, and then like the path that it would trace out, essentially. And so I showed that sort of two hyperbolas being hooked, it can be viewed as maybe part of the trefoil knot. And so as a starter, maybe I could work on this, especially if it's first not at a arbitrary 75-degree angle, but let's rotate this on the x-axis by another 15 degrees, I guess. Okay, so now it's at a 90-degree angle. So I guess I should explain that there's an idea of hyperbolic coordinate systems. Yeah, maybe that'll be a different video. I've worked on that stuff myself a bit, and I think it's in here. So I was noticing that this kind of looks, it's kind of reminiscent of like a saddle point or like a Pringles kind of shape. So I came here for saddle point, was hoping I'd find something about a hyperboloid. Here's a hyperbolic paraboloid. Here's what they call an elliptic hyperboloid, which is what we're looking at. And so you can click here, and they have, actually I clicked here, and you get the hyperboloid page. And so they've got equations. By the way, I mean, this video here does equations. Oh god, add, no. Yeah, so they have the equations there of the equations of the transformations here for an arbitrary, not just 90 degrees, but arbitrary angle to make those hyperboloidal gears. But was kind of interested in can I get the equations of the hyperboloids, or the equations of at least hyperbolas on the surface. So this is part of the thing I'm interested in. I'm curious if they talk about hyperbolic coordinates. So it's kind of like, you know, you've got your polar coordinate systems, you've got spherical coordinates and all that. And I haven't seen much people ever talk about a hyperbolic coordinate system. But I sort of, I think that I came up with one before. Okay, anyway. So, given a hyperboloid, one can choose such that hyperboloid is defined by one of the following. Okay, so they give the equations. That's cool. And so there's two different types. So this, what we're talking about here is a one sheet, and then the two sheet is where it's split into two parts like that. Yeah. And, I mean, some of this one you can get by just taking a hyperbola and just rotating it around the z-axis, right? Okay, so we got some parametric representation. So these equations reminded me of some other equations that may be connected or related. And let me try to bring that up if I can. Do I have those? Let's see here. Well, the trefoil knot itself. So all I'm saying, I don't know. I don't really have more to say than that. These remind me of each other. So look at this. We've got cosine. Oh, that's a that's a hyperbolic cosine. I think I was looking at. Okay, let me go through this ad. I think I was looking at the video. The equations from the video. So let's see if I can bring that up here. Yeah, so... Oh, okay. I think I'm just wrong. I think I didn't realize that this was hyperbolic. But, okay, so... Yeah, I was wrong. So anyway, but imagine, okay, let's pretend. Imagine if this were cosine something cosine and cosine something sine instead of hyperbolic. It's, I think it's reminiscent of the trefoil knot equation. No, it's not. It's not reminiscent. But, hold on, we got one more, the Mobius strip. Hold on here. Equation in here, let's try to find it. Well, here you'll end up, you'll have a cosine times a cosine here, and you'll have a cosine times a sine, and then you have sine here, and it is somewhat reminiscent, although you've got this hyperbolic trig instead, because we do have a cosine times a cosine and cosine times a sine and then a sine, but there's some hyperbolic stuff mixed in there. So I have no idea if these are connected in any way. Sort of interesting to think about, but okay, so hyperboloid. Was there anything else that I wanted to say about this? So there's this relation to the sphere. So, you know, circles and hyperbolas are sort of intimately connected, in my view, because, let's see if I can draw this. Let's say, hold on, let me try to draw this here. Draw mode. Okay, let's say we have this is our coordinate plane. And so I guess we don't really need this the cylinder there. So here's the asymptote. Sorry, this drawing is going to be bad. I'm bad at drawing. Here's the asymptote. So we're going to draw unit hyperbola. Okay, terrible. But we have this point 1, 0. And here's the hyperbola. And there's another, so I believe this would be x squared minus y squared equals 1 is the equation here, I think. And then, so we have, it has an opposite side, right? It has two sides here. Okay. Now, we can also imagine, just for fun, let's draw a unit circle here. And so all of these can be, like any point here could be projected onto the circle, but then it's not quite a mapping one-to-one, right? Because there's nothing over here. But I kind of had this desire, I can't really explain the motivation, but I wanted to like pull these asymptotes back, okay, so that they become the vertical axis here. I wanted some kind of transformation that would pull them back. Okay, and kind of a simple thing to do is that, suppose for an arbitrary, we have this like arbitrary point here that maps onto the hyperbola somewhere. We take basically the half angle, so it'll be over here. So if this is theta here, this will be theta over 2. And there's some kind of map, I sort of forget. But you just double the angle essentially and pull these back. I swear you can do this. I know I'm not being rigorous. I'm not a trained mathematician. And it reminds me a bit of the whole story with electrons and the angular momentum of the electrons, spin 1/2 particles. So if you do that, and then the hyperbola, so instead of x squared minus y squared equals 1, we can say more generally, we can have x squared minus y squared equals z squared, I guess. Z squared, doesn't really matter. But so let's say it's sort of reminiscent of the story with the circle. If we make this 10, I think that these numbers, I think that this will move over here. I forget exactly how it transforms, but by allowing any number here, we get hyperbolas that are out here, and we get hyperbolas that are closer and closer in here. And then if we combine that, so that will cover this entire sort of quadrant, this area over here. Will be covered by this hyperbola. So in a way you could define a point, this is where I'm talking about like hyperbolic coordinates. You could define a point as corresponding to one of these hyperbolas, say like whether you call this a k value or a z squared value. That's you use that as one of the parameters, and the other parameter is, I suppose, an angle theta here would work. Or you could talk about distance along the curve, or you could talk about the area that's swept out. Sometimes they do that. I forget what it's called. Hyperbolic area, something like that. So that would map out. So if we did that on both sides here, we'd be mapping out half of the coordinate plane with hyperbolic coordinates. All we need to do to get the entire coordinate plane with this coordinate system is this pulling the asymptotes back somehow. And I think it's just that you map. Well, you double the angle essentially. You find this theta, and you double it, and it should map things over here. This is also sort of reminiscent or the same thing as, let's do another way of, hold on. Okay, I want to get rid of this. Okay. I think it's sort of equivalent in some sense to the idea. So let's say you had a circle here and a circle here, which, by the way, what I'm thinking of in my head is sort of the beginning of this tutorial. It starts with these two cylinders. These two cylinders, okay? So I'm taking a cross section of that. So anyway, there's two circles. And so you could, here's the center of the circle, but you can have any size circle on the right. So let's say on the right is positive numbers, so you could have a bigger circle and a bigger circle and so on. And same on the left. And so what I'm trying to do is I'm trying to cover the whole surface of the plane. I'm trying to basically create a coordinate system. Obviously, there's multiple ways to make coordinate systems, like there's polar coordinates and all that. But anyway, so we have a radius, which could be positive or negative. On the left side would be a negative radius. So we have some parameter r, and then we have some angle from the center to wherever the point is. And every point on the plane can be sort of coordinatized this way. So even like arbitrarily high up here, you just have this center of the circle, you know, as the points go up here, the center of the circle goes off to infinity in this direction. And there's something hyperbolic here going on somewhere, I swear, because this is sort of like going up here is sort of like when we were talking about on the hyperbola, sort of like trying to go faster and faster towards the speed of light, but you can never reach it, kind of thing. And the center of the circle will go further out. There might be a hyperbolic relationship between the radius and this y coordinate. Maybe that's it. I'd have to look more at it. But I think so. I think this picture is very similar in some way to this story with what I'd like to call these hyperbolic coordinate system, but I've never really seen anyone talk about this specifically, so I don't know. I'd be really interested if it's probably out there somewhere. And okay, so you have hyperbolic coordinates somehow, and let's bring back in this guy. And then, so, or let's say this coordinate system, and this is where you have those cylinders. So let me go into object mode. Let me start making cylinders, like in the tutorial that I've been pointing out. So where's the cylinder? Okay. Let's move this gx -1, and so duplicate gx2, right? We can have a bigger one. So now I talked about how you could coordinatize two-dimensional space with this radius of a circle and an angle, and then you could coordinatize three-dimensional space. Just you have an extra, a z component, an h component, whatever. And so you could start with that. And then you do what they show in this tutorial. So I'll show, I'll just demonstrate how it works. So you go into edit mode, we remove a face, and then I'm going to take these vertices, in the tutorial. So I'm going to rotate by 51.1 degrees, I believe it was. I'm going to take these, rotate in the opposite direction, negative 51.1. All right, and this is a hyperbolic shape. And then I'm going to duplicate that, GX2, rotate along the x-axis by 75 degrees, and then there's a displacement here, minus 0.717, I think it was. Anyway, this is for making those hyperboloidal, what did I say? Hyperboloidal gears. The question is, can this correspond to a different coordinatization? So when I'm talking about a set of coordinates, you know, like when you look at linear transformations, so that's all the possible matrices, essentially, is the same thing as all the linear transformations. You can think of those as transformations of coordinate systems. And so one person might be looking and seeing, well, you're doing these hyperboloidal gears, hyperbolic gears or whatever. But I'm thinking, can this represent a twisting of space, a transformation of space? Is there some kind of equation? Now, I think it's easier to do this when the x, to start with, when these are at right angles of each other, and then to think about an arbitrary angle. But so that's the next step, is thinking about this. And so can I have a coordinatization of 3D space that's represented by this, where I think, you know, it's not hard to see that this looks like the cooling towers in The Simpsons at the nuclear plant or something, but at least before these are twisted, when they're just cylinders, I can imagine that representing a coordinatization, sort of an identity transformation, meaning no change. A coordinate. I say coordinatization because I think that's a sort of accessible word. It's easy to understand, but I don't think it's how mathematicians talk. But if these were just cylinders and not twisted, I can imagine that as the identity transformation, as no change. And what I'm really imagining is that there's all these bigger circles. And now, when you transform it so it's twisted a bit, then I'm not too sure. But, well, as you twist it, see, there's this space that opens up in the center, which is why... so I can't redo because I did something. But that's why this has to... So this twisting of the circle, they call alpha in the tutorial video. And there's a direct... let me try to bring up the math here. Go leave this video a like, please, if you got this far. But they have the equations down here. So theta is the rotation of the object here along the x-axis. And so the idea was, given a radius r, given a height h, and given a theta, can we get the alpha, which is the twisting of the circle? And so, and also the d is this displacement, where you have to so this this rotation theta that I'm about to do is given. Sorry, whoops, what? No. Rx. This rotation right here is given, or this is what we start with. We want to do a 75-degree rotation. And so this, like, if you were an engineer, the advantage of these hyperboloid, I'm going to call them hyperbolic gears, I'm sorry. The advantage of these hyperbolic gears is that they basically can meet together from arbitrary shafts that are in contact, shafts that are at arbitrary angles to each other, right? And so, so that's sort of the input, is that this 75-degree angle between them is what you start with, and you want to create the gears that will match that. So we start with that 75-degree angle, that's theta, and then we're gonna, from the equations, we get the alpha, which is this initial twisting of the cylinder. Here that was we did anyway. It doesn't matter what the number was. There was twisting of that. That's alpha, and so that's the output of the equation. And then there's this d, which is the displacement in the x direction. It has to come over a bit to touch, and that's because there's this space in the middle that is unaccounted for, essentially. So I believe it's negative 0.7. Sorry. GX. Okay. So the question is, can you have a sort of a re-coordinatization, but it's a transformation. But can we have this arbitrary thing where all these circles now also become twisted along with the hyperboloid? Can this correspond to a transformation not just of this cylinder, but of all of space? Can we use this to represent a transformation of space, a sort of twisting of space? And so that would mean coming up with a new coordinate system where for every space, every point in space is accounted for. Basically, I think they're going to be on geodesics, basically like what it's talking about here. I'm thinking of these as geodesics, these paths on the hyperbola. That was what I used to fill the space here. So yeah, every point in space will correspond to some point on this family of geodesics. That's what I'm thinking. Can it be done? That's what I'm thinking about. I don't know the answer. Probably it can be done. Do you know the answer? And so this would maybe somebody can help. But so this is my attempt to make one step forward towards the question of coming up with an equation for the whole trefoil knot. And the idea was that this thing, if somebody knows how to focus on an object, let me know in Blender. Let me know. Just this little part here. Hold on. I can't go into draw mode here. I'm gonna go into draw mode. This little part here is the hyperboloids. Well, it's slightly different because it's a precursor to that. It's like, here's a hyperbola, and then here's a hyperbola. Here's one of the hyperbolas, and before we do this, we're gonna have another hyperbola at a 90-degree angle, and then after that, we somehow push this one down, so that instead of being outside here, it's now connected through here. This is just one part of the trefoil knot, I think. Now, of course, this doesn't work in 3D. It just looks like that. But yeah, that's the idea. That's what I'm interested in. And yeah, I mean, there's this playlist tutorial on YouTube, discrete geometry. But the thing is, this is not really discrete geometry that we're doing here. but I'll mention this this one here. So yeah, Keenan Crane. Some of this stuff I've been searching, actually his papers have been coming up. Probably related to not exactly this problem, but similar other stuff that I'm working on. So actually he talks about geodesics here in the last video, and this is the thing is that the stuff we're doing here is not discrete. There's nothing necessarily discrete about it. And so I'm not really recommending these per se. I think this is a fantastic playlist. I think Keenan Crane is brilliant. He's doing fantastic work. This is amazing stuff. I don't know why I'm really bringing it up. But if you're interested in this kind of stuff, I just think you might be interested in this as well. And I've tried to go through this multiple times, and usually I get somewhere in here and get a little bogged down, and then I get distracted. But then recently I was searching for some specific information, and actually was specifically looking at geodesics, but got smooth surfaces. But there's a lot of information here that might help for sure with this stuff. But differential geometry is related here. We might be able to come up, the equation I ended up finding might be just a partial differential equation. I don't know. So maybe the answer is in some multivariable calculus book that talks about vector fields, or maybe it's some partial differential equation. I don't know exactly. Anyway, I thought I'd just share, and I think there's some other things I wanted to talk about, but I forgot. But I can make more videos in the future. And yeah, let me know what you thought of this. I think some of these things were pretty hard to explain, I think. So if you actually understood what I was trying to say, I'll feel really sort of blessed. Feel free to ask any questions, of course. And just a disclaimer, I'm not saying that I'm the first person to think of this kind of stuff. Like, I don't know why, but when you talk about things online, sometimes people just come in and say, I can't believe you think you're the first person to think about this. And so that's why I'm inserting this disclaimer. I don't know why people do that. So now because I've been attacked in the past, I now say, disclaimer, I do not claim to be the first person to think of this stuff. There's a lot of people out there in the world, and maybe somebody has worked out this stuff already. I'll consult. I have some books on knot theory, and I got a bunch of math books. So I'll consult further, and I'll keep looking on the internet. But anyway, I decided to make this content. So let me know what you think, and I hope you have a good rest of the day. Bye.